The Geography Markup Language is the XML grammar defined by the Open Geospatial Consortium to express geographical features. GML serves as a modeling language for geographic systems as well as an open interchange format for geographic transactions on the Internet. Note that the concept of feature in GML is a very general one and includes not only conventional vector, or discrete objects, but also coverages and sensor data. The ability to integrate all forms of geographic information is key to the utility of GML. GML model. GML contains a rich set of primitives which are used to build application-specific schemas or application languages. These primitives include feature, geometry, coordinate reference system, topology, time, dynamic feature, coverage, unit of measure, directions, observations, map presentation styling rules. The original GML model was based on the World Wide Web Consortium's resource description framework. Subsequently, the OGC introduced XML schemas into GML structure to help connect the various existing geographic databases, whose relational structure XML schemas more easily define. The resulting XML schema-based GML retains many features of RDF, including the idea of child elements as properties of the parent object and the use of remote property references. Profile equals, GML profiles are logical restrictions to GML, and may be expressed by a document, an XML schema or both. These profiles are intended to simplify adoption of GML, to facilitate rapid adoption of the standard. The following profiles, as defined by the GML specification, have been published or proposed for public use: a point profile for applications with point geometric data but without the need for the full GML grammar. A GML simple features profile supporting vector feature requests and transactions, for example with the WFS. A GML profile for GML JP2. A GML profile for RSS. Note that profiles are distinct from application schemas. Profiles are part of GML namespaces and define restricted subsets of GML. Application schemas are XML vocabularies defined using GML and which live in an application-defined target namespace. Application schemas can be built on specific GML profiles or use the full GML schema set. Profiles are often created in support for GML-derived languages created in support of particular application domains such as commercial aviation, nautical charting or resource exploitation. The GML specification contains a pair of XSLT scripts that can be used to construct GML profiles. GML Simple Features Profile. The GML Simple Features Profile is a more complete profile of GML than the above point profile and supports a wide range of vector feature objects, including the following: a reduced geometry model allowing 0D, 1D and 2D linear geometric objects and the corresponding aggregate geometries. A simplified feature model which can only be one level deep. All non-geometric properties must be XML schema simple types that is cannot contain nested elements. Remote property value references just like in the main GML specification. Since the profile aims to provide a simple entry point, it does not provide support for the following: coverages, topology, observations, value objects, dynamic features. Nonetheless, it supports a good variety of real-world problems. Subset tool. In addition, the GML specification provides a subset tool to generate GML profiles containing a user-specified list of components. The tool consists of 3 XSLT scripts. The scripts generate a profile that a developer may extend manually or otherwise enhance through schema restriction. Note that as restrictions of the full GML specification, application schemas that a profile can generate must themselves be valid GML application schemas. The subset tool can generate profiles for many other reasons as well. Listing the elements and attributes to include in the resultant profile schema and running the tool results in a single profile schema file containing only the user-specified items and all of the element, attribute and type declarations on which the specified items depend. Some profile schemas created in this manner support other specifications including IHOS 57 and GML in JPEG 2000. Application schema In order to expose an application's geographic data with GML, a community or organization creates an XML schema specific to the application domain of interest. This schema describes the object types whose data the community is interested in and which community applications must expose. For example, an application for tourism may define object types including monuments, places of interest, museums, road exits, and viewpoints in its application schema. Those object types in turn reference the primitive object types defined in the GML standard. A list of known publicly available GML application schemas is being assembled. Some other markup languages for geography use schema constructs, but GML builds on the existing XML schema model instead of creating a new schema language. GML and KML KML, made popular by Google, complements GML. Whereas GML is a language to encode geographic content for any application, by describing a spectrum of application objects and their properties, KML is a language for the visualization of geographic information tailored for Google Earth. KML can be used to render GML content, and GML content can be a Euro or style Ada Euro using KML for the purposes of presentation. KML is first and foremost a 3D portrayal transport, not a data exchange transport. As a result of this significant difference in purpose, encoding GML content for portrayal using KML results in significant and unrecoverable loss of structure and identity in the resulting KML. Over 90% of GML structures cannot be transformed to KML without loss or non-standard encoding. Similarly, due to KML's design as a portrayal transport, encoding KML content in GML will result in significant loss of KML portrayal structures such as regions, level of detail rules, viewing and animation information, as well as styling information and multiscale representation. The ability to portray placer marks at multiple levels of details distinguishes KML from GML, since portrayal is outside the scope of GML. GML geometries GML encodes the GML geometries, or geometric characteristics, of geographic objects as elements within GML documents according to the vector model. The geometries of those objects may describe, for example, roads, rivers, and bridges. The key GML geometry object types in GML 1.0 and GML 2.0 are the following: point, line string, polygon. GML 3.0 and higher also include structures to describe coverage information, the raster model, such as gathered via remote sensors and images, including most satellite data. Features GML defines features distinct from geometry objects. A feature is an application object that represents a physical entity, for example a building, a river, or a person. A feature may or may not have geometric aspects. A geometry object defines a location or region instead of a physical entity, and hence is different from a feature. In GML, a feature can have various geometry properties that describe geometric aspects or characteristics of the feature. GML also provides the ability for features to share a geometry property with one another by using a remote property reference on the shared geometry property. Remote properties are a general feature of GML borrowed from RDF. An XLINK of attribute on a GML geometry property means that the value of the property is the resource referenced in the link. For example, a building feature in a particular GML application schema might have a position given by the primitive GML geometry object type point. However, the building is a separate entity from the point that defines its position. In addition, a feature may have several geometry properties, for example an extent and a position. Coordinates coordinates in GML represent the coordinates of geometry objects. Coordinates can be specified by any of the following GML elements. GML has multiple ways to represent coordinates. For example, the element can be used as follows. Note that, when expressed as above, the individual coordinates are not separately accessible through the XML document object model since the content of the element is just a single string. To make GML coordinates accessible through the XML DOM, GML 3.0 introduced the AND elements. Using the element instead of the element, the same point can be represented as follows. The coordinates of a geometry object can be represented with the element. The element is used to represent a list of coordinate tuples, as required for linear geometries. For GML data servers and conversion tools that only support GML1 or GML2, there is no alternative to. For GML3 documents and later, however, and are preferable to. For more information on the SRS name attribute, see Coordinate Reference System below. Coordinate Reference System equals. A coordinate reference system determines the geometry of each geometry element in a GML document. Unlike KML or Geo or SS, GML does not default to a coordinate system when none is provided. Instead, the desired coordinate system must be specified explicitly with a CRS. The elements whose coordinates are interpreted with respect to such a CRS include the following. An SRS name attribute attached to a geometry object specifies the object's CRS, as shown in the following example. The value of the SRS name attributes is a uniform resource identifier. It refers to a definition of the CRS that is used to interpret the coordinates in the geometry. The CRS definition may be in a document or in an online web service. Values of EPSG codes can be resolved by using the CRS registry service operated by the Oil and Gas Producers Association, OGP at http://www.epsg-registry.org. The SRS name URI may also be a uniform resource name for referencing a common CRS definition. The OGC has developed a URN structure and a set-specific URNs to encode some common CRS. A URN resolver resolves those URNs to GML CRS definitions. Examples: polygons, points, and line string objects are encoded in GML 1.0 and 2.0 as follows. Note that line string objects, along with linear ring objects, assume linear interpolation between the specified points. Also, the coordinates of a polygon have to be closed. Features using geometries equals. The following GML example illustrates the distinction between features and geometry objects. The building feature has several geometry objects, sharing one of them with the survey monument feature. Note that the reference is to the shared point and not to the survey monument, since any feature object can have more than one geometry object property. Point profile equals. The GML point profile contains a single GML geometry, namely an object type. Any XML schema can use a point profile by importing it and referencing the subject instance. Note that when using the point profile, the only geometry object is the object. The rest of the geography is defined by the photo collection schema. History Initial work, to OGC recommendation paper equals, Ron Lake started work on GML in the fall of 1998, following earlier work on XML encodings for radio broadcasting. Lake presented his early ideas to an OGC meeting in Atlanta, Georgia, in February 1999, under the title XGML. This introduced the idea of a geodom, and the notion of geographic styling language based on XSL. Akifumi Nakai of NTT Data also presented at the same meeting on work partly underway at NTT Data on an XML encoding called GXML, which was targeted at location-Euro-based services. In April 1999, Galdos created the XBED team. XBED was focused on the use of XML for geospatial. This led to the creation of SFXML with input from Galdos, US Census, and NTT Data. Galdos demonstrated an early map-style engine pulling data from an Oracle-based GML data server at the first OGC Web Map test bed in September 1999. In October 1999, Galdos Systems rewrote the SFXML draft document into a request for comment, and changed the name of the language to GML. This document introduced several key ideas that became the foundation of GML, including the 1. Object Property Value Rule, 2. Remote Properties, and 3. The decision to use application schemas rather than a set of static schemas. The paper also proposed that the language be based on the resource description framework rather than on the DTDs used to that point. These issues, including the use of RDF, were hotly debated within the OGC community during 1999 and 2000, with the result that the final GML recommendation paper contained 3 GML profiles, two based on DTD, and 1 on RDF, with one of the DTD unregistered trademark S using a static schema approach. This passed as a recommendation paper at the OGC in May 2000. Moving to XML schema, version 2. Even before the passage of the recommendation paper at the OGC, Galdos had started work on an XML schema version of GML, replacing the RDF resource scheme for remote references with the use of XLINK, and developing specific patterns for handling extensions for complex structures like feature collections. Much of the XML schema design work was done by Mr. Richard Martel of Galdos, who served as the document editor and who was mainly responsible for the translation of the basic GML model into an XML schema. Other important inputs in this timeframe came from Simon Cox, Paul Daisy, David Burgraff, and Adrian Cuthbert. The U.S. Army Corps of Engineers were quite supportive of the development of GML. The U.S. Army Corporation of Engineers sponsored the AEUSL Pilot project, which was very helpful in exploring the utility of linking and styling concepts in the GML specification, with important work being done by Money and Xia Li. The XML schema specification draft was submitted by Galdos and was approved for public distribution in December 2000. It became a recommendation paper in February 2001 and an adopted specification in May of the same year. This version eliminated the A-OE profiles from version 1 and established the key principles, as outlined in the original Galdos submission, as the basis of GML. GML and GXML as these events were unfolding, work was continuing in parallel in Japan on GXML under the auspices of the Japanese Database Promotion Center under the direction of Mr. Shigeru Kono. GXML and GML differed in several important respects. Targeted at LBS applications, GXML employed many concrete geographic objects, while GML provided a very limited concrete set and built more complex objects by the use of application schemas. At this point in time, GXML was still written using a DTD, while GML had already transitioned to an XML schema. On the one hand, GXML required the use of many fundamental constructs not at the time in the GML lexicon, including temporality, spatial references by identifiers, objects having histories, and the concept of topology-based styling. GML, on the other hand, offered a limited set of primitives and a recipe to construct user-defined object types. A set of meetings held in Tokyo in January 2001, and involving Ron Lake, Richard Martel, OGC staff, Mr. Shigeru Kono, Mr. Akifumi Nakai and Dr. Shimada led to the signing of an MOU between DPC and OGC by which OGC would endeavor to inject the fundamental elements required to support GXML into GML, thus enabling GXML to be written as a GML application schema. This resulted in many new types entering GML a unregistered trademark S core object list, including observations, dynamic features, temporal objects, default styles, topology, and viewpoints. Much of the work was conducted by Galdos under contract to NTT Data. This laid the foundation for GML3, although a significant new development occurred in this time frame, namely the intersection of the OGC and ISO TC 211. Towards ISO, GML 3.0 broadens the scope of GML while a basic coding existed for most of the new objects introduced by the GML-GXML agreement, and for some introduced by Galdos within the OGC process, it soon became apparent that few of these encodings were compliant with the abstract specifications developed by the ISO TC/211, specifications which were increasingly becoming the basis for all OGC specifications. GML geometry, for example, had been based on an earlier and only partly documented geometry model, and this was insufficient to support the more extensive and complex geometries described in TC/211. The management of GML development was also altered in this time frame with the participation of many more individuals. Significant contributions in this time frame were made by Milant Ninick, Ron Lake, Richard Martel. On June 12, 2002, Mr. Ron Lake was recognized by the OGC for his work in creating GML by being presented the Gardels Award. The citation on the award reads OE in particular, this award recognizes your great achievement in creating the geography markup language and your uniquely sensitive and effective work to promote the reconciliation of national differences to promote meaningful standardization of GML on a global level. Simon Cox and Clemens Portil also subsequently received the Gardels Award, in part for their contributions to GML standards. The Open Geospatial Consortium is an international voluntary consensus standards organization whose members maintain the Geography Markup Language standard. The OGC coordinates with the ISO TC 211 Standards Organization to maintain consistency between OGC and ISO standards work. GML was adopted as an international standard in 2007. GML can also be included in version 2.1 of the United States National Information Exchange Model. ISO 19136 ISO 19136 Geographic Information. Geography Markup Language is a standard from the family ISO of the Standards for Geographic Information. It resulted from unification of the Open Geospatial Consortium definitions and geography markup language with the ISO 191XX Norman. Earlier versions of GML were not ISO conformal with GML version 3.1.1. ISO conformity means in particular that GML is now also an implementation of ISO 19107. The geography markup language is an XML encoding in compliance with ISO 19118 for the transport and storage of geographic information modeled according to the conceptual modeling framework used in the ISO 19100 series and including both the spatial and non-spatial properties of geographic features. This specification defines the XML schema syntax, mechanisms, and conventions that provide an open, vendor-neutral framework for the definition of geospatial application schemas and objects. Allow profiles that support proper subsets of GML framework descriptive capabilities. Support the description of geospatial application schemas for specialized domains and information communities. Enable the creation and maintenance of linked geographic application schemas and data sets. Support the storage and transport of application schemas and data sets. Increase the ability of organizations to share geographic application schemas and the information they describe. See also, GML application schemas, City GML, geographic data files, SOSI, well-known text, ISO TS 19103 Euro conceptual schema language, ISO 19108 Euro temporal schema, ISO 19109 Euro rules for application schemas, ISO 19111 Euro-spatial referencing by coordinates, ISO 19123 Euro coverages, GeoSPARQL Euro GML for geospatially linked data and the semantic web. References. External links, ISO 19136 2007, Geographic Information, Geography Markup Language, GML Specifications, GML 3.1 Specification, Digital Earth, GeoWeb, GeoRSS, Geographically Encoded Objects for RSS Feeds, Recommended XML GML Encoding of Common CRS Definitions, Open Geospatial Consortium, Demonstration of a Coordinate Reference System Registry, Open Geospatial Consortium, a nearly official coordinate reference system registry from the OGP, Oil and Gas Producers Association, C++ data binding for GML, GML point profile OGC public document, free GML viewer, GeoWeb conference, conference dealing with GML, KML etc. Lesson on GML from Penn State University, basic information for GML, ISO publicly available schema for GML 3.2.1/ISO 19136, fact sheet 19136.